Right now, while you're watching this, a telescope a million miles from Earth is doing something human eyes have never done. It is staring down a star so bright it would blind every older instrument. And beside that star, for the first time in human history, there is a planet. Not a flicker, not a guess. A real, honest, captured by light, orbit-confirmed world. With clouds, with chemistry, and possibly with something stranger hiding underneath. Here is the hidden story of what James Webb has already seen, and the worlds nobody fully explained. Welcome back to Proof, where we uncover the hidden truths of the cosmos. If you're new here, hit subscribe now, because what you're about to hear, most people will never know. Drop a comment right now and tell me where you're watching from. I read everyone. For most of the last 30 years, catching a real picture of a planet outside our solar system was almost a joke among astronomers. They knew these planets were out there. Thousands of them, by 2024, had been confirmed by the tiny gravitational wobble they cause in their parent star, or the faint dimming of starlight when they pass in front. Those tricks work. They tell you a planet is real. They tell you roughly how big it is. They tell you how close it orbits. But they do not show you the planet itself. They do not give you a cloud. They do not give you a color. They do not give you a single honest photograph. Getting that photograph is brutal. Think of it this way. A star is a stadium floodlight. A planet is a single candle floating next to that floodlight. Both are millions of miles away. From out here, the candle is invisible. The floodlight drowns it completely. So for years, every direct photograph of an exoplanet was either a blurry smudge near a young, dim brown dwarf, or a rough estimate stitched together out of raw data and called a portrait. That is not a real image. Not in the way you would call a picture of Jupiter a real image. Not in the way you would call a Hubble portrait of Saturn a real image. To make a real one, you need two things working together. You need an enormously precise mask that physically blocks the floodlight so the candle can finally show up. And you need a mirror sharp and sensitive enough to grab the tiny leftover photons, the packets of light bouncing off the planet. A coronagraph is the mask. A coronagraph sits inside a telescope and throws a tiny artificial eclipse over the star so any dot nearby can be seen. That is the same trick the original coronagraph on Earth did for the sun. Solar astronomers used it to study the sun's outer atmosphere, called the corona, during an eclipse. Now that same idea, miniaturized and computerized, sits inside the James Webb Space Telescope. And Webb's main mirror is over 21 feet across, far larger than anything we sent into space before. Webb sees an infrared light, the kind of light your eyes cannot see, but your skin feels as warmth. Infrared cuts through dust the way a kitchen window lets you see steam on a stove. For cold, distant planets that mostly glow in infrared anyway, that is perfect. Put the coronagraph and the giant mirror together and you have the first camera ever pointed at another solar system with a real chance of seeing the candle. In August of 2022, a team at NASA, working with the Space Telescope Science Institute in Baltimore, decided the moment had come. The target was a planet called HIP 65426b. The name looks like a license plate because it is built from the catalog entry of its star. HIP-P comes from the Hipparcos catalog, a database of nearby stars put together by a European satellite in the 1990s. 65426 is the star's number in that list. The lowercase b means it is the first planet found orbiting that star. HIP 65426b sits roughly 385 light years from Earth. A light year is the distance light travels in 1 year, almost 6 trillion miles. That is far. But to Webb, it is close. The planet itself is a gas giant, somewhere between 6 and 12 times the mass of Jupiter, depending on which follow-up measurement you trust. Jupiter is the largest planet in our own solar system. If HIP 65426b sat inside our sun's family, it would be hard to miss, but it orbits a young, bright star about 100 times farther from that star than Earth is from our own sun. That distance is what allowed Webb to finally see it. In early September 2022, Webb's near-infrared camera called NIRCam and its mid-infrared instrument called MIRI both locked onto the system. Each one used its coronagraph to throw a tiny artificial eclipse over the host star. Then, the engineers at the Space Telescope Science Institute processed the raw frames, removing the residual starlight speckle pattern that any telescope, no matter how good, leaves behind on its sensor. The picture that came out, 4 separate panels at 4 different infrared wavelengths, showed 4 little dots, all in roughly the same place on the sky, all moving together around the same point of light. That was the planet. Real, distinct, repeatedly captured at multiple wavelengths. Not a smudge, not a guess. A world, finally, on a real photograph. NASA released the images on the 1st of September 2022. It was the very first direct image ever taken by James Webb of a planet orbiting another star. And it would not be the last. It was, in fact, only the visible part of the iceberg. Because if Webb could take a picture, it could now aim a spectrograph at any dot already photographed, the same dot at multiple wavelengths, and pull out the chemistry. That opens every nearby world to direct, molecule by molecule, multi-wavelength study. Here's the twist almost nobody talks about. The first direct image was supposed to celebrate how Webb could literally see another world, and it did. But the picture was not pretty. The little dot was so small in the frame that even the sharpest press release image looked like something you might accidentally see in a headlight glare. The jaws that dropped inside the astronomy community were not dropping because of the picture's beauty. They were dropping because of what the picture meant. For 30 years, every claim about an exoplanet had to come with a careful footnote. The planet is real. We cannot show you a photo, but the orbit math is rock solid. Here's a graph of the wobble. Here is a graph of the dip. Now that footnote could finally be removed. Webb had shown in pixels that exoplanets have actual positions in space. They can be located, they can be re-aimed at, they can be photographed again under different filters at different times. That unlocked everything that came next. Because once you can see a planet, you can point a spectrograph at it. A spectrograph splits light into a rainbow. Every chemical in the planet's upper sky, every gas in its atmosphere, leaves a fingerprint in that rainbow. Read the fingerprints, and you have the planet's recipe. That is what Webb started doing. Almost immediately, planet after planet. By late 2023 and into 2024, the Webb team was hitting exoplanet after exoplanet with the same trick. Split the light, read the rainbows. Tell the world what is in the sky of a world tens or hundreds of light years away. The results were surprising for how often they broke expectations. Not occasionally. Almost every time. One of the first big surprises came from a planet called K2-18b, sitting roughly 124 light years from Earth in the constellation Leo. K2-18b had been on astronomers' short list of exciting worlds for years. It is about 2.6 times the size of Earth, which puts it in a strange in-between category called a sub-Neptune. Sub-Neptune means smaller than Neptune but bigger than Earth. We do not have a planet like it in our own solar system, so we had no first-hand clue what its atmosphere would look like. Some models said it was a small Neptune with a thick hydrogen envelope. Others said it was a water world, entirely covered in deep ocean under a heavy steam sky. In 2023, a team at the University of Cambridge, led by astronomer Niku Madhusudan, pointed Webb's NER spec and its near-infrared imager at K2-18b during two separate transits, the moments when the planet crosses in front of its star from our point of view, briefly dimming starlight. As the starlight filters through the planet's outer atmosphere on the way to us, different gases absorb different colors of light. The pattern of those missing colors is the fingerprint. Madhusudan's team reported methane and carbon dioxide in the atmosphere and very little hydrogen, which by itself was already weird. Most hydrogen-rich sub-Neptunes would not show that pattern. The simplest explanation was that K2-18b did indeed have a dense, hydrogen-rich sky, and underneath that sky, hidden from sight, a global ocean. That was twist one. A water world candidate, suddenly not theoretical. Then, in April of 2025, Madhusudan's team pushed harder. They published new analysis claiming they had detected dimethyl sulfide, or DMS, in K2-18b's atmosphere. Dimethyl sulfide, in plain language, is a molecule made of carbon, hydrogen, and sulfur. Here on Earth, almost every molecule of dimethyl sulfide floating in our air comes from phytoplankton. Phytoplankton are tiny ocean plants, so small you cannot see them without a microscope. They live in the sea. They are alive. When they bloom and die, the breakdown of their cells releases DMS into the air. On Earth, life makes nearly all of it. So if DMS is in the air of another planet, the simplest explanation is also life. The Cambridge team said the signal was strongest at about 1 part per million by volume. Tiny, but real. They said this was the second strongest biosignature hint ever recorded on a planet outside our solar system. Biosignature means a chemical fingerprint that, on Earth, is made only by living things. The press ran with the headline, "The world held its breath." People read the news, looked up, and felt something they had not felt in a long time. A serious, peer-reviewed team at a serious university was saying the quiet part out loud. Maybe we are not alone. Maybe we can already see the proof. Maybe, just maybe, the universe has neighbors, and we have finally caught their breath. Then came twist two. By August of 2025, a separate team, this one led by astronomer Raphael Luque at the University of Chicago, published a response in the journal Astronomy and Astrophysics. Luque's team reanalyzed the same Webb data on K2-18b, the same transits, the same instrument files. The conclusion was different. They could not find a robust dimethyl sulfide signal. They argued the original DMS reading could be explained by normal star noise, by imperfect subtraction of the star's own light, and by chemical pathways in the upper atmosphere that do not require biology. They pushed back hard. A NASA-led study in late 2025 reached the same general direction. Stronger data was needed. The strongest hint yet, suddenly, was not so strong. Madhusudan, to his credit, did not walk back the word. He simply said the question is still open, and the next round of Webb observation will decide it. So here is where K218b sits at the moment. There is methane, there is carbon dioxide, there is a hydrogen-rich sky above what may be a deep ocean. And there may or may not be dimethyl sulfide leaking from that ocean. Whoever wins, this is real science. A question is being asked in public. 2 serious teams are weighing evidence. Nobody is faking anything. But the chemistry of a tiny dot of starlight, filtered through an alien sky, is being held up to the light, molecule by molecule, with the most powerful instrument humanity has ever built. That is the hidden truth underneath the headline. Not whether life is there, the fact that we are checking. The fact that the question is finally being asked with instruments that can answer it. And the lesson, the deeper one, is what scientists call equifinality. Equifinality is the idea that very different starting conditions can lead to very similar looking end states. In plain words, several different paths can lead to the same chemical fingerprint. Sometimes biology, sometimes weird geology, sometimes an atmosphere cooked by starlight. Until you have ruled out the other paths cleanly, you cannot honestly say which one is real. Before Webb, almost every article about the TRAPPIST-1 system sounded like a fairy tale. TRAPPIST-1 is a tiny, dim, ultra-cool red dwarf star about 40 light years from Earth. TRAPPIST stands for Transiting Planets and Planetesimals. Small telescope, the small robotic telescope in Chile that first caught the original planets back in 2016 and 2017. Around that little star, astronomers confirmed 7 rocky worlds, several of them sitting right inside what they call the habitable zone. The habitable zone is the ring of distance around a star where temperatures are mild enough for liquid water to sit in an open pool. Not boiling, not frozen, just liquid. That is what we want when we search for life as we know it. Earth sits inside the habitable zone of our sun. TRAPPIST. One looked, on paper, like the closest thing to a second home we had ever found. Magazine covers, conference talks, science documentaries, all featured renderings of those 7 little worlds. Some of them had names, some of them had imagined clouds, imagined oceans, imagined skylines under a small red sun. Then Webb looked. In 2023 and 2024, Webb turned its mid-infrared instrument toward TRAPPIST-1b and TRAPPIST-1c, the 2 innermost planets. A team led by Thomas Green at NASA Ames Research Center in California published the result. The 2 innermost planets had no detectable atmosphere. None. Not thick, not thin, just bare rock. A bare rock around a tiny red star is not a friendly place. The star, even though it is cool, is also violently active. Red dwarfs flare. They send out huge bursts of radiation, far more often and far more violent than our sun does. If there ever was an atmosphere on TRAPPIST-1b, the star would have stripped it. Slowly at first, then all at once. Without an atmosphere, there is no air. Without air, there is no liquid water on the surface. Without water, no life as we know it. A dream, on paper, became a desert in real life. That was twist 3, and it landed hard. To be fair, the outer TRAPPIST-1 worlds D, E, F, G, and H have not all been measured yet. Some of them receive far less radiation from the host star. It is possible, though not proven, that one of those outer planets has managed to hold on to a thicker sky. Green's team and follow-up teams are still working through it. But the mood across the astronomy community shifted. Suddenly, having the right distance from the right star was not enough. A planet also needed to be close to a quiet kind of star with a calm, stellar wind, with a low flare rate, and with a long enough stable history for an atmosphere to survive. That filters the list of candidate worlds, and a lot of those candidates do not pass the new filter. TRAPPIST-1 was the perfect classroom. Example of that lesson. The system that had looked for nearly a decade like humanity's best hope for a nearby second Earth turned out to teach the field an entirely different lesson. Hope is not data. Atmosphere is data. And when the atmosphere is missing, the dream collapses, whether we like it or not. While all of that was happening, almost in parallel, Webb was quietly solving a different mystery that nobody had asked it to solve. The mystery of WASP-39b. WASP-39b is a hot Jupiter. Hot Jupiter is the nickname astronomers use for a gas giant that orbits very close to its parent star, so close that its upper atmosphere gets cooked by heat. This particular hot Jupiter sits about 700 light years from Earth. It was one of the earliest exoplanets ever measured in detail by Hubble's predecessor, the Spitzer Space Telescope. By 2022, the JWST team, led by Hannah Wakeford at the University of Bristol and a long list, of collaborators was using Webb's near-infrared spectrograph to break the light of WASP-39b's atmosphere into a rainbow. The early results were startling. They spotted water vapor. They spotted sodium. They spotted potassium. They spotted carbon monoxide. They spotted methane, carbon dioxide, sulfur dioxide, all of it mapping out at slightly different altitudes in the atmosphere. Each gas in the rainbow came from its own altitude, because in a gas giant, the deeper you go, the hotter it gets, and the heavier molecules sink lower in the sky. So splitting the rainbow by altitude was, in a sense, taking a three-dimensional scan of an atmosphere no human will ever fly through. And then they spotted sulfur dioxide, written chemically as SO2. Sulfur dioxide is not strange on Earth. We make small amounts of it in volcanic eruptions. We make some of it in industrial pollution. But on WASP-39b, the amount of sulfur dioxide was huge, and the chemistry that would make it was not simple. Outgassing from the surface of the planet, the way volcanoes work. The only path to make that much sulfur dioxide that fast was photochemistry. Photochemistry means chemistry driven by light. Ultraviolet light from the parent star was breaking apart other molecules in the planet's upper sky, and the broken pieces were recombining into sulfur dioxide on the fly. This was not theoretical. This was happening in real time in a sky 700 light years away. A team led by Diana Powell at the University of California, Santa Cruz published the result in Nature in 2024. The paper was a landmark. For the first time, astronomers had a clean, repeatable signature of photochemistry happening on a planet outside our solar system. Photochemistry is the same family of reactions that on Earth builds and rebuilds our ozone layer over and over. Ozone means 3 oxygen atoms stuck together. Without photochemistry, there would be no ozone. Without ozone, the sun's ultraviolet radiation would be deadly on the surface. So the discovery on WASP-39b was not just about that weird hot world, it was a proof of principle. Photochemistry is a universal planetary process. It plays out on hot Jupiters, on temperate rocky worlds, on Earth, on worlds we have not yet discovered. That scientific point has a quiet, big meaning. When we eventually point Webb, or its successors, at a small rocky planet around a quiet star and look for biosignatures in its sky, photochemistry will be part of the noise we have to subtract. We will need to understand what light alone can do before we can say with confidence what life is doing. So every weird world Webb studies now, even the scorched, hostile ones, is teaching us a tool we will need to search for life properly later. WASP. 39b was not a bust. It was a practice round for the real exam. By now, surely through all of these stories you might reasonably ask, what about Proxima Centauri b? It is the closest rocky planet we have ever found outside our solar system, just over 4 light years away. Proxima Centauri is the nearest known star to our sun, tiny, red, a red dwarf, prone to flares. But around it sits Proxima b in the habitable zone. Found in 2016, Proxima b instantly became the first place any future interstellar probe would visit in a dream. If life is anywhere, surely we would look there first. The problem is glare. Proxima b hugs its host star. From Earth's point of view, the planet is lost inside the dazzling floodlight of the star. Webb can detect its presence by measuring how the planet tugs the star around with gravity. Webb can read a rough temperature, but Webb cannot break the planet's atmosphere into a rainbow the same way it did for K218b or WASP-39b. Not yet, not with the current generation of tools. The star is simply too loud. Proxima b sits closer to its parent star than Mercury sits to our sun, which means it is bathed in red light and infrared glow from a noisy neighbor. Some proposals to use Webb's coronagraph on Proxima have been published, but the odds are not in their favor. Real answers about Proxima b's atmosphere will probably wait until a much larger, much more advanced telescope, one with a bigger mirror or a more aggressive light-blocking mask, finally launches. Until then, Proxima b will sit on the cosmic doorstep, close enough to dream about, close enough to point at, far enough away to keep its largest secrets all to itself. And there is a second concern baked in. Proxima Centauri erupts. Red dwarf stars are famous for stellar flares, sudden bursts of high-energy radiation that can be thousands of times stronger than anything our sun produces. If Proxima b ever carried an atmosphere, those flares, mounted over millions and billions of years, easily have the cumulative power to erode it entirely. The European Southern Observatory, working with the Atacama Large Millimeter Array, a huge array of 66 radio dishes in northern Chile that work together as one giant telescope, published modeling work in 2024 suggesting that even moderate flare activity could in principle strip Mars-sized atmospheres around Proxima b in, well, under 1 billion years. Add a possible tidal lock, the gravitational trap that keeps one face of a planet permanently facing its star, and you have a world where any surviving water might be locked in ice caps on the dark side, and any thin surviving atmosphere might only cling to a narrow terminator ring, the twilight band between endless day and endless night. That is a haunting picture, tantalizingly close, likely cold and weather-blasted, possibly, and this is the pinch, partly alive. Now zoom out. All of these worlds taken together point toward one quiet, unsettling truth. The galaxy is full of planets. By 2024, the count had passed 5,500 confirmed exoplanets. Most of the new ones were spotted by NASA's TESS mission, the Transiting Exoplanet Survey Satellite, a small telescope launched in 2018 that surveys the whole sky for transits, looking for the tiny moment a planet crosses in front of its star. But the count is not what matters. What matters is the pattern. Across hundreds of studies now, the typical planet in the Milky Way is not a strange thing. It is a familiar thing. A small rocky world, or a mid-sized sub-Neptune, or a gas giant sitting around a middle-aged star in some kind of stable orbit with some kind of atmosphere. Statistically, our solar system is not unusual. Statistically, somewhere out there, there should be cousins of Earth. Not one, many. Common, in fact, may not be the right word. By 2026, working from Kepler and TESS statistics, astronomers estimate that on average, every star in our galaxy hosts at least one planet. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. Multiply that out. There are more planets in our galaxy than there are grains of sand on all of Earth's beaches. That is not a poetic exaggeration. That is a published estimate from the 2021 consensus paper by astronomer Kento Masuda and colleagues, updated in 2024 with newer TESS and microlensing data. The galaxy is bursting with worlds. So why is no one answering? That is the heart of the great silence. Every ingredient we know life as we know it to need keeps showing up out there. Water vapor, carbon, hydrogen, nitrogen, sulfur, phosphorus, rocky surfaces, stable temperatures, sunlight of various kinds. The kitchen is fully stocked, the pantry is full, but the meal has not been served. Astronomers have started giving this silence a careful name. They call it the Great Silence Problem. They frame it as a question. Is life genuinely rare among planets? Or are we simply not yet sensitive enough to see the fingerprints it leaves behind? The honest answer, right now in 2026, is that we do not know. The most likely explanation is a mix. Some planets are too hot, some are too cold. Some have atmospheres that were stripped by their star. Some have atmospheres that are too thick to read clearly. Some are buried in dust. Some have geologies that bury their biosignatures underground. Some may have life in forms we have not learned to recognize. Life that breathes iron instead of oxygen, or life that eats hydrogen and exhales methane, or life that does not have chemistry like ours at all. The more we look, the more cautious we get. The more cautious we get, the better our instruments have to be before we can say anything with confidence. A small handful of researchers have started leaning toward a quieter, less satisfying explanation. Perhaps the jump from simple chemistry to genuine self-sustaining biology is just harder than we hoped. Perhaps we are rare, not unique, just rare enough that the two closest answers are too far away for our current ears to hear. There's a name for this idea too. It is sometimes called the rare Earth hypothesis, and it has been around since the late 1990s when paleontologist Peter Ward and astronomer Donald Brownlee wrote a book of the same name. Webb's findings are not killing that hypothesis. They are sharpening it. If you want a single honest number to anchor the silence, here it is. Several studies, the most recent published in 2025 by a team that ran numbers on the current Webb biosignature yield, estimate that roughly 90% of potential biosignature planets around M-dwarf stars, small red stars like TRAPPIST-1 and Proxima Centauri, are likely to have their atmospheres either stripped or hidden from current instruments. The same model suggests the remaining 10% will be the places where astronomers focus. Their next decade of effort. K218b is 1, TOI 700d, a planet about 100 light-years away in the constellation Dorado, maybe another. The field is narrowing. Here's the part they did not put on the magazine cover. The same JWST instruments that are generating these stories are also generating the strongest reasons to doubt them. A single photon counting error in one detector channel can look like a telltale gas, a subtle starlit artifact, a faint feature of the host star that gets partially attributed to the planet, can look like a chemical abundance. That is the honest mess inside this work. Every Webb biosignature claim is being challenged, replicated, refit, doubled, and sharpened. Nobody is rushing. The community knows the stakes, and they know the cost of faking a headline. The famous cautionary tale in this field is the Mars meteorite ALH 84001, found in Antarctica in 1984. In 1996, a NASA team announced microscopic structures inside the rock that looked like fossil bacteria. The U.S. president at the time, Bill Clinton, gave a televised speech about it. 18 months later, most scientists had concluded those tiny shapes were not biology. They were mineral patterns. The headline still echoes. The lesson still teaches. Webb teams live with that memory every time they announce, which is why every clean exoplanet image, Webb takes matters for a different reason. The pictures are not just pretty. They reveal the cloud structure, the temperature layering, the chemistry, in ways that chart papers and wobble graphs never could. And the spectrographs are not just producing pretty rainbows. They are producing hard data, molecule after molecule, day after day, that future scientists will reanalyze for decades. The Hubble Space Telescope, launched in 1990, is still producing exoplanet science today, more than 30 years later, by being used as an archive. Webb's archive will be longer, when a graduate student in 2050 runs a new analysis on one of today's Webb spectra using a planet formation. Model that has not been written yet, they will still be answering questions this data first raised. That is the kind of return on investment science rarely gets. Webb is a one-shot investment that will still be teaching new things decades after the last pixel is taken. If hidden stories like this are why you come here, subscribe now because we are just getting started. Let me zoom out one more time and ask the question out loud. What does the existence of these direct images really mean for us, sitting on this one wet rock? Think about what it really means that a machine we launched on a rocket in 2021 is now pulling individual photons out of a dark sky, photons that left planets tens or hundreds of light years ago, photons that bounced off those planets' clouds, slipped between their molecules, crossed the cold nothing between stars, and landed on a mirror we built. We are now reading off the chemistry of worlds we will never visit. We are now writing their weather forecasts. We are now comparing their stars to our sun and asking, quietly, is anyone looking back at us? That is not a small shift. That is the largest shift in the human view of the cosmos since Galileo first aimed a telescope at Jupiter and saw 4 tiny moons he had not been told were there. That night, 400 years ago, changed the conversation forever. It proved our solar system was not special, that other worlds orbited another planet, that the universe was bigger than what we were told. Tonight, the conversation is shifting the same way, only deeper. JWST's direct images are proof of the same kind of shift. There are other worlds. There are other skies. There are other clouds, other storms, other weathers, other chemistries. We have already begun to outline them. We have not yet heard their answer, but we are listening. And the choice to listen, the choice to keep building instruments like Webb, the choice to keep pointing them at the sky for years on end, is itself one of the most quietly hopeful things our species has ever decided to do. Not because we are guaranteed an answer, because we are guaranteed a question worth asking. That is a gift we are giving ourselves. The first honest, photographed light from another planet is the gift of knowing we can finally see. The Habitable Worlds Observatory, planned to launch in the late 2030s or early 2040s, will have a mirror almost twice as wide as Webb's and coronagraphs that are an order of magnitude better at blocking starlight. The Nancy Grace Roman Space Telescope, also slated for the late 2020s, will survey the sky for exoplanets using gravitational microlensing, a technique that lets astronomers spot planets whose gravity briefly bends and brightens the light of background stars. Together, those instruments will triple, perhaps quadruple, the number of directly imaged exoplanets within 10 to 15 years.